MATLAB provides many different facilities with regards to running simulations. And in this example, and all of the examples we're looking at here, for the most part, we're focusing on simulating systems of ordinary differential equations forward in time. We're going to focus on this two-compartment model with the bolus as our case study, and then we're going to do modifications to this in order to demonstrate how different inputs can be applied to this specific system. So when we look at the two-compartment system, we see that we have two different states. We have the state Cp, which represents the concentration of the drug in the plasma, and At, which represents the amount of drug in the tissue. And in this example, we're considering the initial condition of the system in the absence of any inputs. So our initial condition here is going to be 0 for both the drug in the plasma compartment and the amount of drug in the tissue compartment. We also have three different outputs. Our first output is going to be the concentration in the plasma. The second output is going to be the amount of drug in the tissue compartment. And the third output is going to be the total amount of drug in the system. So for this example, we have 4 parameters. We have the bolus that occurs at time 0 with a magnitude of 50 moles, and we have 3 different outputs. In order to make it simpler to construct simulations in MATLAB, what I've done is I've put together a complete set of files that basically contains everything you need to run simulations in MATLAB. The way that these 4 files work together is shown in the diagram on the right, and the arrows between them show the passage of information. Okay, so each of these are sort of encapsulated in their own way, and they call each other. And I will describe in detail each of the files and how we can edit and change these files. But what I want to talk about now is sort of the big picture, or the process overview of how simulations are run within MATLAB. So if we start at the bottom and sort of work our way up, the first model and all of these files are located in the examples directory, and they're under the two-compartment with bolus directory. So if we begin with the file ode_model.c, so this is a C file, so it means it's written in C, and this is analogous to the .4 file that you may be accustomed to if you've used adapt, if you have experience with adapt. Basically, within the C file, you define the set of ordinary differential equations, you define your outputs, and you define your initial conditions and other information about the system. Okay? And one thing that's important is that, just like in adapt, you have to compile it before it can be used. So if you make changes to it, you have to understand that you must recompile the C file before those changes will take effect. Okay, so this C file is meant to speed up calculation, and the way it speeds it up is it basically calculates the derivatives of your system at any given point in time. So in order to integrate the system forward in time, what we're going to do is we're going to call a Simulink model. The ODE_simulation.mdl file is a Simulink model, and what it does is it sends into the ODE_model.c file a set of initial conditions, x0, a set of inputs, u, and the set of states, so the current state at any given point in time, x. And what ODE_model.c does is it returns, it's a function, it returns a vector of derivatives and a vector of outputs. Okay. To run the simulation, in order to run the simulation, what I've done is I've created this file called run_simulation_generic.m. So what this function does is it facilitates running simulations. Basically, you give it a data structure called simulation options and a set of parameters, and it will manage the starting and stopping of the simulation and running it forward in time, and it will return the value of the states within your model, and it will also return the output values as well within your model. Okay, so assuming that run_simulation_generic works as it's planned, then you should never have to edit this file in any way. You should never change it. You should just call it. Okay? the way that it works is it takes different inputs. These could be your parameters. These could be different initial. This could be your continuous infusions, time varying information. It sends that, your initial conditions, and the desired output times into ODE simulation. And ODE simulation then goes and returns the value of the states x, the outputs y, and the vector of times t corresponding to the x's and the y's. What you can modify is something called simulation underscore driver. So simulation underscore driver is basically a script that will, given a set of parameters and a data structure called simulation options, call run simulation generic. And after it calls run simulation generic, it takes the output, which is returned, the sim output by run simulation generic, and then it does something with it. So what you do with the output is going to depend on what you're trying to do. If you're just simulating the system and you want to say you're doing a sensitivity analysis and you're just modifying parameters in some sort of looping fashion, then you may want to plot this output. If you're performing a parameter estimation, like we'll see in the next section, then you may want to evaluate your system at specific points in times where you have observations, and then you will use those predicted values to construct your objective function. So this is the big picture. These are the 4 files you need to know or need to have to run a simulation. You will edit only 3 of them. You'll edit ODE underscore model.c. You'll edit possibly ODE underscore simulation.mdl, and you will edit simulation underscore driver.m. So before we get into any of the details, I need to discuss some terminology and to establish what these words mean. Okay, so on the previous slide in the figure, I had inputs going into the system. So when I say inputs, I'm not necessarily referring to physiological inputs. You know, a physiological input is a bolus value, like when you're administering the drug in a bolus fashion or a continuous infusion. What I'm referring to when I talk about inputs are model inputs. Okay, so these are all of the information that's passed from the simulation driver file down through into the model file. Okay, so these model inputs can include physiological inputs, except boluses. They can include parameters that you're estimating. They can include parameters that you're not estimating that you just want to fix and pass on down into your simulation. They can include time varying information and other constant information. Okay, so when I refer to inputs, I'm not necessarily referring to physiological inputs. I'm referring to model inputs. I also refer to the states. In the previous slide, I said that the x's that are being returned or passed around, those are state values. A state is a general term that I'm going to use to describe anything that is defined by a differential equation. So anything that evolves in time is going to be considered a state. When we look at compartmental modeling, the compartments themselves are states, but not all states are going to be compartments. So if you have a disease progression model that describes the evolution of a tumor over time, or describes the evolution of a disease over time, those are going to be states as well, but not necessarily compartments. We're going to basically begin at the bottom of that diagram we started off with, and we're going to work our way up. And in order to start with that, we need to discuss how models we need to discuss the C programming aspects of MATLAB. So before I talked about, in the previous section, I discussed how to write functions in MATLAB and how to write scripts in MATLAB, and all of the programmatic information about how to define variables and how to access arrays only applied to MATLAB. But when we're editing this ODE underscore model.c file, we need to understand that we are actually using C. Okay, so much like the Fortran models that we have in ADAPT, the models here are written in C because they're going to be much faster. Okay. They're also not going to be used directly. You're not going to run them directly, so they have to be compiled first. So in in adapt, whenever you create a model, you have to link it, and here you're going to have to compile it. And the way that you compile models in MATLAB is you use the MEX command. So MEX is a built-in MATLAB command, and basically at the command line or the command prompt or within a script, you can type MEX and a file name .c, and what that's going to do is that's going to take your C source code and it's going to compile it into an executable library. Depending on the operating system you're using, it'll create a different file extension. So if you're on OS X like I am, and you MEX the ODE model.c file, what it's going to do is it's going to create a file called ODE_model.mexmaci. And if you're doing it on Windows, the binary file that it creates will be ODE_model.mexw32. Okay. So remember, if you make changes to the C file, in order for those changes to take effect, you have to recompile the C file. Because if you make changes to the C file and you don't recompile it, and you run your model, it will just use the previously compiled version, which will not contain your changes. The way that I minimize my own personal errors, because I tend to make lots of them, is I put a command at the very top of my scripts that basically it's just a MEX command that MEXes whatever C file I'm using. The purpose of this is that every time you run your script for some sort of analysis, you recompile it. It only takes a few seconds, but it prevents you from forgetting to recompile your model when you've made changes to it. So there are different rules you need to learn. Just like when you program in Fortran, there are different rules you need to learn when you program within C. If you look at the very top, the code listed in red, the double A is equal to 2.0 semicolon, int A is equal to 3 semicolon, and dx 2 in brackets is equal to 4.0 semicolon. These are 3 statements in C. Okay. One thing you'll notice is that in order to end a statement, you have to use a semicolon. So what C is going to do is it's going to read a statement from the beginning of the line all the way to the semicolon. And then after that, it'll start reading for the next statement and the next statement. Okay. So the semicolon basically ends a statement. Now there are no columns in C, so you can put text anywhere you want to within a C file. In order to use variables in C, you have to declare them. This is basically what you do in Fortran. At the top of your at the top of each subroutine, before you use a variable, you have the real star or whatever, and basically what you're doing is you're declaring a variable. So here what we're doing is, and if you look at the first command, double space capital A is equal to 2.0 semicolon. What I've done here is I have declared the variable A, and at the same time I've set it to a value of 2.0. Now it's not necessary to set it to a value, but I like to initialize all my variables to some value, even if they're 0. What you should also note is that C is a case-sensitive language. So capital A here is a double, while lowercase a here is an integer, and they are very different variables. Okay. The easiest mistake I think to make in C is to not understand that floating point numbers and decimals are different, and that in order to assign something to a floating point number, it's not good enough just to call it a double. When you assign it to a value, you actually have to give that number a decimal. So double A is equal to 2 is not good. Double A is equal to 2.0, that is good. And also note that if you're taking a variable within a statement in C and you're dividing it, so if you divide like a number by a variable, so if I tried to create 1/2, if I wrote 1 divided by capital A, that would not necessarily give me a value of 0.5. I would have to write 1.0 divided by capital A in order to get me a value of 0.5. Lastly, what we need to talk about is that indexing of arrays begins at 0. So in Fortran and in MATLAB, indexing of arrays begins at 1. So in order to access the first element of an array or a vector within MATLAB or Fortran, I would use the index of 1. But within C, I need to use the index of 0. So what does this mean? This means that in this example, dx and then the 2 in brackets means that I'm talking about the third element of the array dx. So I'm assigning the third element of the array dx to 4. So that's basically what you need to know in order to get started in programming in C for the purposes of these examples. So what I want you to do now is within MATLAB, I want you to open the file ode_model.c, and I'm going to open it as well in MATLAB. Now, if we edit this file in MATLAB, the first thing we'll notice is that on the very first line, we have to define the ODE function name. So basically, you're probably not going to change the name of this file, but if you were to change the name of this file, the prefix before the .c extension would have to be consistent with the actual S function name here. So if you change the name of the file, you'll have to change the name here as well. In C, as in Fortran, there are different subroutines or functions that the user can define. And basically what this file does is it has 4 different functions or subroutines. They're listed on the handouts. The first is MDL initial sizes, the next is MDL initial conditions, the third is MDL derivatives, and the fourth is MDL outputs. So basically what we need to do is we need to define information about the system, number of inputs, number of outputs, number of ordinary differential equations. We need to give it a default set of initial conditions. Then that's what MDL initial conditions does. MDL derivatives then defines the derivatives of the function, and MDL outputs then defines the outputs. This is very, very similar to the different subroutines used in adapt. So if we look at MDL initial sizes, you can see that here. You'll see that there's lots of different variables here, but really the only thing that you need to worry about are three different values that you need to set. Num_const states is the number of continuous states. So in our example, we have a 2-compartment system, so we have a value of 2. Num inputs is going to be anything that's passed to the function from the outside. So we'll discuss in a little detail what this is, but basically it's the number of parameters, the number of constant values sent in, the number of piecewise continuous inputs, and the number of infusion rates, all added together. If you remember, all we have in this system is 4 parameters, so we're just going to set this value to 4. And then the last thing that we have is the number of outputs. The number of outputs here is, if you recall, the plasma concentration, the mass of drug in the tissue, and the total amount of drug in the system. So the number of outputs here is 3. The next function that we have to edit, if we ever want to customize this, is we have to give it a default set of initial conditions. These are the initial conditions for each state within the system. Now, what you need to understand is that this is something that MATLAB requires, but it's easily overwritten, and in fact we will override it. But because it's required, we have to give it some value for each state. Remember, indexing begins at 0. So our first state is x0 of 0, and our second state is x0 of 1. And what I've done here is I've assigned them to the value of 0, and we could overwrite this if we wanted to, and I'll discuss where we would do that later. But we just have to provide MATLAB with something. If we look at both the MDL outputs and if we look at the MDL derivatives subroutines, we'll see that each of them has a common block. That's what I call it. Basically, it's a block of code that's common to both the outputs and the derivatives section. And what this is where we take our inputs, our states, and our derivatives, and we map them to variables that are convenient to use. So our inputs in this situation are u's. Okay, so u0 is going to be our first input, u, and in brackets 1 is the second, 2 is the third, and 3 is the fourth. And what I'm doing here is I'm just defining the variables vc, k12, k21, and kel. So I've declared these variables, and I've placed the inputs into those variables. So whatever the first input is will be placed in vc. Whatever the second input is will be placed in k1, 2, and subsequently whatever the last input is, which is the u of 3, will be placed in kel. The next thing I'm doing is I'm defining derivatives for each state. So I'm saying that dCp is going to be equal to 0 and dAt is going to be equal to 0. And I'm also defining the states themselves. So Cp is going to be my first state, or x of 0, and At is going to be my second state, or x of 1. The way this works is, this is very similar to creating temporary variables within adapt to remap things back and forth. So this is my suggestion. This is not a requirement. You could write your ODEs in terms of u's and x's and dx's if you wanted to, and this is effectively, you know, what you could do in adapt if you were to use the p's and the xp's and the x's as well. But my suggestion to you is to do this, because as the model grows in complexity, this is going to become very, very important. So what we can see here is the derivative section, and if you notice that the comment block here is the same in the derivative section as it was in the output section. So it's important, I believe, to stress here that when you make changes in the comment block in one area, you need to copy and paste them down over the comment block in the other area. So if I make changes in the derivative section, I need to select all of these from the beginning to the end, go up to the output section and then paste this over it. Copy this and paste it over it. And if you make the changes in the output section, you need to copy them and paste them down here. Again, for this example, it's very simple, but as things become more complicated and confusing, it's going to be very important that you try to maintain consistency between these two blocks. So in the output section, I define the outputs in terms of the states that I had mapped. So when I say mapped, what I've done here is I've mapped the first state to the temporary variable Cp, and the second state to the temporary variable At. And while I initialized my derivatives here and here, they actually have a value of 0. Now I need to calculate those derivatives. So then I'm going to reassign those to a value. And here I'm assigning those to a value in terms of the parameters I've created and the states. So here I've just basically typed out my derivatives. Then what I need to do is I need to remap these back to their C equivalent. So these values are used within the subroutine, the dCp, the dAt, the Cp, and the At. Those are all used within the subroutine, but after the subroutine is called, those values are lost, so they need to be remapped into the C equivalents. So that means I need to put the derivative of Cp into the first derivative, or the first element of the derivative vector, and then I need to place the value of the derivative of At into the second as well. Now we'll go back up to the output section. And here I'm just defining my outputs in terms of the temporary variables that I've created. So the first output is the plasma concentration, the second output is the tissue, the mass of the drug in the tissue, and the third output is the total mass of drug currently in the system. So that's an overview of the different parts of the C file that you need to modify or understand in order to construct models in MATLAB. The next thing I want to talk about is the Simulink model. So ODE_simulation.mdl is a Simulink model, and as I said before, what it does is it actually integrates your system forward in time. So it takes a vector of initial conditions, a vector of inputs, u, and a vector of states, x. It sends those to the ODE_model.c file, and then it uses the ODE_model.c file to calculate the values of the derivatives and the values of the outputs at any given point in time. So what we need to do is we need to first understand a little bit about what Simulink is, and this is the definition from the MathWorks. From the MathWorks, basically Simulink is an environment for multi-domain simulation and model-based design for a dynamic and embedded systems. Basically what it is it's a graphical environment for constructing models, and because it's a graphical environment for constructing models, there are basically different blocks, and you can use these blocks as you see fit to construct your system. One of the nice things about Simulink from my perspective is it allows you to model both in the time domain and the Laplace domain simultaneously. But there's many, many different things you can do with Simulink. And what I'm going to do is I'm going to show you the bare minimum that you need, and then as you encounter more complicated problems, you'll learn more about Simulink as you start to use MATLAB. From the MATLAB window, I can type Simulink. What this is going to do is it's going to bring up the Simulink library. And these are all of the different blocks that you can use within Simulink. So over here on the left are different groupings of blocks. Here are the most commonly used blocks. These are blocks that involve continuous systems. There's different math operators. There's many kinds of blocks. And for this system, we're only going to need to learn about 6 different blocks, and I'll talk about those in detail. But the way you create a model is you click on this little icon to create a new model, and then you can just drag blocks from the Simulink library over to this model. So, for example, sources, or basically inputs into the system, we can just say we want to add a constant source, we just drag it over and drop it. And you can do this with all of the different blocks. So what I want to talk about are the specific blocks that you are going to use in the examples today. So the first one we're going to talk about is the constant block. Basically, this specifies inputs that are not going to change. Your parameters are being sent into the simulation, and for the purposes of the simulation, they're not going to change. So they're an example of a constant block. During estimation, we will change those parameters, but for any given simulation run, these parameters do not change. If we have time-varying inputs, like infusion rates, these are going to be fed into the system using the from workspace block. This is basically it's a block that can hold a vector of values and corresponding times, and then it's going to fit those together through linear interpolation. It can be useful to concatenate or combine multiple signals in MATLAB, and to basically, if you have 2 different signals and you want to combine them into one, you're going to use the mux block. Similarly, if you want to take a signal that has multiple components and you want to break it up into its constituents, you can use the demux block. The system function, or S function block, is what we're going to use to identify our differential equations. And if we need to pass the outputs back to the workspace, we will use the output block. This is going to contain all the little y's when we're simulating our system forward in time. So if we open up the ODE_simulation.mdl file in MATLAB, we can do this by either double-clicking on this file, or we can type ODE_simulation in the MATLAB command window. So if we open up this file, what we're going to see is that this is probably the simplest Simulink model we're going to use. We're using 4 different blocks here. We're using the parameters block. This is going to hold our system parameters. This is the VC, K12, K21, and KEL values. We have a mux block. Well, we're basically just saying we're just passing a signal through, the parameter signal through. We have the S function block here, which contains our ODE model, and then we have our output, which is going to contain the y's in our system. What I want to do is I want to double-click on the mux block. So, first we'll start by looking at the parameters block. If we double-click on this, we'll see that it's a constant block, as indicated by the constant value here. What we can do is we can set it to a value, but what we want is we don't want to set it to a single value. We want to be able to modify values externally and send those modified values. So what we're going to do is specify the value, the name parameters. Parameters is actually a MATLAB variable that's going to be created. So what you can see here is that we can actually place a variable that's created within MATLAB here as a constant value and not just a number. Next, if we look at the mux block, what we need to do is we need to be able to specify the dimensionality of the different inputs. Okay. So in our system, we have 4 parameters, right? So we could just put the number 4 here, and then it would understand that the first input into this mux block is going to be a 4. Now, say we want to modify our system and we want to add parameters to it later on. if we added a parameter or reduced the number of parameters by 1 or 2, then we would have to come back and replace that number. But instead what we're doing is we're using the MATLAB length command. What length does is length will dynamically size this input to whatever the length of parameters is. So currently it's 4. So length of parameters will return 4 in this case. Next we'll look at the S function block. Basically we have to give it the model name. Remember, this is the very first line. This is defined in the very first line of the ODE_model.c file, and it's also the prefix of the base file name of the C file. Now here it's not actually referencing the C file, but rather it's actually referencing the compiled version of the C file. So in my case it's ODE_model.macci or something like that. So it's not actually talking about the C file itself, but it's actually talking about the compiled version. And then the last is the output. This is going to contain the different outputs specified in the model C file. So that's basically the format of the Simulink model for this specific example. Now again, this is the example where we have a two-compartment system with bolus values being inputted into it. Now, what I want you to do is to consider how bolus values are actually applied. Or basically, I want you to understand some of the details associated with running simulations. In this example, what I have is a system with at least 2 states, and I want a bolus applied to state 1 at time 0, and I want a bolus applied to state 2 at time 15. The bolus in this case applied to state 1 at time 0 is going to have a value of 3, and the bolus applied at time 15 to state 2 is going to have a value of 10. What I want you to consider is how this is actually occurring. So if all of your boluses apply at time 0, then basically what you have is you have an initial condition change at time 0. If your boluses are applied or administered at different times other than 0, what you have to do from a mathematical perspective is at each time there's a bolus applied, you have to stop your simulation, and then you have to add a value to that state in which the bolus is applied. So in this example, what we would have to do is we would have to set the initial condition of state 1 to a value of 3. Then we would have to integrate the system forward in time until we got to time 15. At time 15, we would have to stop the system. We would have to take the value of state 2 at that point in time, add a value of 10 to it, and then restart the integration with that as a new initial condition starting at time 15. Okay. So you can do these things manually in MATLAB if that's what you want to do. But what I've done is I find that that's a very tedious process, and so what I did is I created this file called run_simulation_generic.m to facilitate simulating systems forward in time. And what I try to do is I try to anticipate the different types of inputs that people would find useful or that they would need, and then I wrote this M file with that in mind. So again, this is a file that you really don't have to edit, or you shouldn't have to edit. If you choose to, you're more than welcome to, but in general you're probably not going to want to edit it. And what it does is it handles all of the logistics and all of the mechanical aspects of integrating a system forward in time. If you want to call it, basically you need to give it 2 different arguments. You need to give it the first argument as a vector of parameters, and then the second argument is something called simulation options. Okay, and if you want to edit the simulation_driver.m file, this will show you how we define these simulation options. But based on the contents of these variables, run simulation generic will then integrate the system forward in time, and then what it's going to do is it's going to take the results of that simulation and place them in the variable called SimOutput. If we look at the inputs, parameters is just a vector of parameters, and simulation_options is a data structure. Okay. SimOutput is also a data structure, and it has 3 different fields. It has a field called T, which corresponds to the output times, and this is something that you're going to define in simulation options. It has a field called X. This is a matrix. This matrix has rows that correspond to the times. So if the t field has 10 rows, if you specified 10 different output times, then SimOutput.x is going to have 10 rows as well, and it's going to have a column for each state. SimOutput.y is also going to have the same number of rows as t, and it's going to have a column for each output that you specified in the model. So you might be asking yourself at this point, what is this simulation options thing, and what do I have to do with it? Well, simulation options is a data structure, and what I've tried to do is I've tried to define clearly what the different components of that data structure are. You need to specify the output times. So there's a field called output times, and this is going to be a column vector of times. And this is basically the time points in which you want your simulation to be evaluated. There's going to be, you need to specify the model file. This is a string. So basically you need to specify the base file name of the Simulink model that you want to integrate forward in time. So by default, this is going to be ODE_simulation, not without the .mdl extension, and you're not going to change that. Then we need to specify the initial conditions of the system. So this is a vector of the initial conditions. Remember, the first element in this vector is going to correspond to x0 of 0 within the C file. The second one is going to correspond to x0 of 1. The third one is going to correspond to x0 of 2, and so on and so forth. These are the required fields that you need to simulate a system forward in time. There are optional fields as well. The optional field that is important is the default_simops. This can be used to control different aspects of the simulation. So say you want to specify your simulation solver, your ODE solver to use. By default, I believe MATLAB uses ODE45, but if you feel that your system of equations is particularly stiff, you can shift it from ODE45 to ODE23S, and there's different aspects that you can customize about simulating the system. If you go to the slide number in your handouts in the advanced topics section, I give examples of how to use this particular field in simulation options. The first thing you're going to want to know is how do we for this example, we need to know how to have a bolus input. What you do if you want to create a bolus input is you have to create a field under simulation options called bolus_inputs. This is a field where you have a column for every bolus event. So if we look at the previous example, we had a bolus event at time 0, and we had a bolus event at time 15. Okay, so the first row basically corresponds to the times in which there are bolus events. For every state where a bolus event occurs, you need to have 2 rows. Okay, so here we have a bolus event occurring in state 1 and a bolus event occurring in state 2. The bolus event occurring in state 1 is at time 0, and the bolus event occurring in state 2 is at time 15. So at every time there's an event, for each state that it receives a bolus, you need to put the magnitude of the bolus that occurs at that time. So for example, at time 0, state 1 has a bolus value of 3 applied to it, but at time 15, state 1 has no bolus event applied to it. Similarly, at time 0, state 2 has a bolus value of 0 because there's no bolus value applied at time 2. However, at time 15, state 2 has a bolus value of 10 applied to it. If there were more states, if this was a system that had 20 different states, you don't have to worry about the other 18 states because they're not having any bolus events. You just have to have 2 rows for each state that has bolus events. One thing that I think is important to discuss here is the concept of initial conditions and time 0. So the initial state field actually specifies what the values of the states are at the initial condition. But the initial condition depends on the system itself. Okay, so basically the initial condition applies at either the first output time or the first time there is a bolus value that is applied. So for example, if you were to apply a bolus value at time 2 and your first output time was time 3, then the initial state would apply at time 2. If you were to apply a bolus value at time 15 and your first output time was 0, then the initial condition would apply at time 0. This is important because if you're modeling disease progression, sometimes your first measurement or your first bolus administration is going to occur at a time much later than your first than your actual initial disease state. So, for example, if we're considering the tumor growth model, a lot of the tumor growth models are modeled from the beginning of a study. So when the study begins, when the inoculum of cancer cells are placed in an animal, that's time 0. And if we're estimating the initial condition, we need to evaluate the system at time 0. So the way that this is done is we add a time where the initial conditions actually apply, and then we run the simulation with this extra value, and then we remove these extra times from the sim output. So we will discuss an example of this in the estimation section, and you can see the slide number if you want to jump ahead and see an example of how this is done. So the last thing we need to discuss here is the MATLAB script called simulation_driver.m. Basically, what simulation_driver.m does is it defines your parameters, it defines your simulation options, it calls run simulation generic, and then it takes the output from run simulation generic and does something with it. In this case, we're just plotting the results because this is just an example of how to simulate an ODE system. If we consider simulation driver.m, this is basically the script that we're using to run our simulation. So the first thing that we do is we just clear all of the variables within the workspace, and then I have my little mex command here to compile my model in case I made any changes to it. Then I have a vector where I'm defining my parameters. So this is BC, K12, K21, and KEL. Then what I need to do is I need to set up the simulation options data structure. So I define my model name, I define my initial state, and then I define the simulation_options.output times. So basically what I'm saying here is I want my output times to go from 0 to 5 in 1,000 increments. So I want a very smooth output profile. And then I need to define my bolus value. Now remember, I had a bolus value of 15 moles, and I need to divide that by the volume of the central compartment. So I take my 50 and I divide it by my very first parameter, parameters 1. And this is going to go into state 1. Then I run the simulation using run_simulation_generic. The first argument is parameters, the second argument is simulation options, and then I store the information in sim output. And then the rest of this is fairly straightforward. I'm going to close all the figures that are currently open, then I'm going to open a figure, and then I'm going to go through and I'm going to use subplot to plot the plasma concentration, the mass of the tissue site, and the total drug present within the system. Now if I click on this button here, I can run the simulation, and we can see the output. Here we have the natural log of the plasma concentration, we have the amount of drug in the tissue, and we have the total amount of drug in the system decaying. So let's consider lines 43 and 44 of this example. If you see, what I'm doing here is I'm using the plot command, and I'm plotting SimOutput.t. That's the vector of output times. These correspond to the output_times field in simulation options. Then I'm plotting SimOutput, and I'm plotting .y, which is my model outputs defined in the output subroutine. This says that I want to plot all rows. Now keep in mind that the rows in y correspond to the rows in t, and that I want to plot output 2. So if we were to kind of look at the contents of these different fields, we would see that t is a column vector, and in this case n is going to be 1,000 because we said we wanted 1,000 different increments. The first column in y is going to be CP, the second column in y is going to be AT, and that's what this plot command refers to here, the second column. And the third column in Y is going to be the total amount of drug. Similarly, if we look at SimOutput.x, the first column is going to be the first state, and the second column is going to be the second state. So x1 here is x0 in C, and x2 here is going to be x1 within C. So this is an example of how to simulate the two-compartment system with the bolus. Now what I'm going to do is I'm going to go through different examples in MATLAB to show you how to add different types of inputs, different model inputs, not necessarily physiological inputs. So how to add different model inputs into the system. To do this, we're going to have to change between different directories. And if you're editing files in one directory, and then you change to another directory, and then you save those files that you're editing in that new directory, it'll overwrite them. And sometimes MATLAB doesn't seem to respect the fact that you've changed directories. So in general, it's good to close all of the files you're editing before you switch from one directory to another, because the files are all named the same. I use the same naming convention for all of these different examples. If you want to make sure that you're not going to overwrite anything, what I would do is just, as we go from one example to the other, I would close MATLAB and then reopen it and then change to the new directory. I think that would make more sense. So close all the files, close MATLAB, then reopen MATLAB and change to the new directory, and that'll make sure that there's not any problems here. I've shown you how to have bolus values inputted into the system. Now what I want to talk about is how to add both rates of infusion, how to pass constant information, and how to add time-varying information to the system. So this is these are the different required fields in simulation options, the ones with the stars, and then here are our ways of passing both physiological and parametric inputs into the system from our simulation driver. So these are the different fields that you would have to add. We just discussed the bolus events field. Now we're going to go on to infusion rates, passing constant information, and passing time-varying information. So I'd ask that you restart MATLAB and change into this directory to _compartment_with_infusion. So what we're going to do now is, starting with the two-compartment model with the bolus, we're going to discuss how we modify that example in order to add an infusion. And then we're going to discuss how we modify that example in order to add constant information, and also how to modify that example in order to add time-varying information. It's good to start off with the model structure, or the description of the parameters, and the equations that we're using. So we're effectively using the same set of equations we were before, except we've added two inputs. We've added inputs into the plasma compartment, and we've also added an infusion input into the tissue compartment. We still have two different states, CP and AT, and we still have three different outputs: the plasma concentration, the tissue, the mass of drug in the tissue, and the total amount of drug in the system at any given point in time. So we're using the same sort of approach that we were using before. We have a simulation driver. Simulation driver is going to call run sim generic, and run simulation generic is going to run the ODE simulation simulink model, and the ODE simulation simulink model is then going to call our compiled form of the C model. So what we're going to do is just start at the top and look at the modifications we'll have to make as we go down. So basically, the way that we specify rates of infusion is we create a field called infusion_rates. Okay, this is a vector, and each element of the vector is going to have two fields. It's going to have a name field, and it's going to have a vector of levels. And what we're trying to implement here is shown on the right. So we want to infuse the drug into the plasma space from 0 to 5 at a level of 6. and we want to infuse the drug into the tissue compartment from 8 to 14 at a level of 12. So basically every time you add an infusion rate, you're going to have to make modifications both to Simulink and the C file as well, and we'll discuss those specific modifications for this example. So the first thing we want to do is we want to modify simulation options. So what we're doing is we're going to add two different elements to infusion rates. So we're creating infusion rates 1, and we're going to give it a name called drug P, and then we have to specify the levels. This is the levels, and this is the times and the rates in which the levels shift. So at time 0, it jumps to 6, and then at time 5, it goes down to 0, and it stays constant till the end. Then we have to specify the second set of infusion rates. So we create a second element infusion rates. We're going to name that drug T, and at time 8 the infusion rate is going to go up to 12, and at time 14 it's going to go back down to 0. So these names, drug P and drug T, will be used within Simulink. The way that we do this is we have to add two different from workspace blocks. So if we open up the ODE_simulation in this particular directory, you'll see that there's the parameters block. Remember, the parameters block is a constant block. And then we have to add two from workspace. We have a from workspace for the first drug infusion, and we have a from workspace in the second drug infusion. Notice that the name here, drug P and drug T, is the same as the name field whenever we created this particular entries in the simulation options. So to add this infusion rate in the Simulink, we have to add infusion_rates dot and then the name, drug P and drug T. Now we have this mux block, and what it's going to do is it's going to take this signal here of parameters with a width of 4, and it's going to add to that signal this signal of infusion rates into the plasma compartment with a width of 1, and this signal of infusion rates into the plasma compartment of width 1 as well. So when we double click on the mux block, it's going to bring up this number of inputs. Remember, length of parameters is exactly the same as it was before, and then we have to add a 1 for each subsequent input. So this 1 here corresponds to drug P, and this 1 here corresponds to drug C. So the order here goes from top to bottom, and it corresponds from left to right here. Next, we need to modify the model file. So we have our 4 inputs that are the parameters, and then we added 2 more inputs, 1 for each infusion rate. So we have to change the number of inputs from 4 to 6. Then in the common block, we need to map those 2 inputs to something that we can use within our differential equations. What I've done in the common block here is I've created a variable called drug P, and that's going to take the 5th input, or U of 4, and drug T, which is going to take the 6th input, or U of 5. Then we have to modify our differential equations. You see where I've added the drug being administered into the plasma compartment here, so it's drug P divided by VC, where drug P was defined in the common block in both the outputs and the derivative section. And I've also added the mass of drug being administered into the tissue compartment, drug T here. And then if we run the simulation driver, we'll get an output that looks like this. You can see the first infusion followed by the second infusion, and then you see the dying off. You see the first infusion being applied here into the central compartment, and then the second infusion being applied here into the tissue space, and then here's the total drug as well. Here's the simulation driver, and if we click run, first it's compiling the model, and then it's running it. So basically, if you remember, I have the model name, the initial condition, and the output times. These are all the same that we had from the previous example, and then I've defined the infusion rates vector, and then I've run the simulation here. And then I go through and I just plot everything like I did before and dump it to a file. And this is the solution. So for this example, you're going to close MATLAB and you're going to restart MATLAB, and you're going to change to the two compartment with constant directory. The purpose of this example is to show you how to pass information from your simulation driver all the way down into your model file, and this information is information that doesn't change. So the reason why I think this is useful is I like to take data and I like to enter the data in one location. So if you have information in your C file and then you use that information in subsequent analysis. So say you're doing say you're using KD values and you want to use those KD values within your model, but then you also want to use them when you're plotting, and you want to use them maybe whenever you're doing some sort of summary statistics after you've done your analysis. And for me personally, I prefer to place these values in one location so that if I make a mistake or if I want to adjust them, I only have to adjust them in that one location. So when I do this, I typically pass these values down as constant from my upper level analysis script all the way down into my model. So this is an example of how you would pass constant information that doesn't change. This is because of the way that simulations are run, this is actually equivalent to passing your parameters down. Because even though during a parameter estimation, or if you're doing a sensitivity analysis, your parameters are going to change, for any given simulation, your parameters generally don't change. So in this example, this is an example I've contrived, and I said, what if we want to be able to pass some value down to our simulation to inhibit the rate of elimination? So what I've done is I've included this variable called fmod, and what fmod does is it can either inhibit or enhance the rate of elimination of the drug. So basically fmod here just multiplies by KEL. So this is basically our bolus, our two compartment model with a bolus, and we're passing a constant piece of information along as well. The first thing we have to do is we have to modify simulation driver. We have the bolus specification here as our simulation option. Then we add another simulation option called myConst. Okay, myConst is very similar to the infusion rates in that there's a field for the name. So myConst1 is the name is fmod, and then there's a value associated with it. So instead of having a vector of values, we just have a single value associated with it. In this case, 0.1. So what this is going to do is this is going to reduce the KEL by 90%. Then, because we're adding an input here, we need to add a block in Simulink. So we create a constant block here, and we have to name the name of the value that goes in the constant block is myconst.fmod. So all of your constants are going to have a myconst variable name dot and then the constant name. The constant name is the name you specified on the previous slide. And then similar to the infusion rates, for every input we add, we have to add a number of inputs in the mux block. So we have the length of the parameters as before. That's going to be a value. That's going to have a value of 4. And then as we go from the top to the bottom, we have to add numbers. So we add a 1 here for the myconst. So this input here corresponds to the second entry in the number of inputs to the mux block. So next we have to change our number of inputs. Before we had 4 inputs, but now we have an extra one, a constant, so now we have to change that to a value of 5. So we change the number of inputs to 5. Then in the common block, I want to map fmod to that 5th input. So fmod here is a variable I'm creating. It's a double, and it's gonna take on whatever is in the 5th input, or u of 4. And then I have to modify my differential equations accordingly. So I have a minus fmod times KEL here. So I've taken this constant value in the upper level and I've passed it down to the lower level all the way into the C file where the integration is occurring. And if we run this, it'll run forward in time, and we'll see that the drug hangs out a lot longer in this example than it did before. Again, this is a contrived example, but it shows you, I think, pretty clearly how you can take information that's defined in your simulation driver and pass that information down into your actual model file, into the C file where your integration is occurring. The last example that we're going to talk about is how to send time-varying information into the system. So if you want to run this, you need to go into this directory, and you run it the same way you run all of these examples. You just open the simulation_driver.m file, and you just run that script. So sometimes you're gonna most of the inputs that I use and that most people use are either going to be a bolus into the system, an infusion, or some sort of constant value, and that may satisfy most of your needs. But occasionally you're going to want to be able to specify something a little bit more complicated. And so what I've done here is I've created a method for sending time-varying information. Basically, what it does is it takes a vector of times and a vector of values corresponding to those times, and then Simulink will linearly interpolate between those points. Now, if you make the time values really, really small, or the increments between the time values really, really small, then you'll get basically a very smooth profile going into your system. So in this case, what I wanted to do is I wanted to consider a system where we have some sort of a circadian rhythm, right? So if we have our system where we're adding a bolus value into the central compartment, but the compound has some sort of there's some sort of endogenous production within the tissue space, and in this case the endogenous production is equal to sine of t plus 2. So if we look at our differential equations, the differential equation for the plasma compartment doesn't change in this case. The only differential equation that changes is the differential equation for the tissue space, where we've added this sine of t plus 2 component. Now keep in mind that our initial conditions before were 0, but because there's some sort of endogenous production, we actually have to solve for our initial conditions at time 0. So we can set these ODEs equal to 0, and we can solve for CP and AT at time 0, and we'll find that that at time 0 the plasma concentration is defined in terms of the volume of central compartment and the rate of elimination, and that at time 0 the amount of drug in the tissue space is defined by K12, K21, and the rate of elimination as well. Again, we have the same sort of outputs. We have Y1, which is the plasma concentration, Y2, which is the tissue concentration, and Y3, which is the total drug present in the system at any given point in time. Here are the 4 parameters we're looking at. We're looking at a BC of 1, K12 of 10, K21 of 10, and KEL of 5. We want to look at how the system responds to boluses at times 10, 20, and 30 of magnitude 50. And we have this endogenous production at the tissue site. So what we do here is we first define our parameter vector, and then this is in the simulation driver, so this is all in MATLAB, right? Then we define our initial conditions for the plasma concentration and for the tissue concentration. We define them in terms of our parameters. Then we define our initial state and simulation options as CP0 and AT0. Now these were previously defined at lines 10 and 11. Next, we need to specify when we have boluses. Our bolus times are 10, 20, and 30. They are values of 50 each, and they all go into state 1. Now remember that these bolus values are in moles, and we need to convert them into concentration. So what I do is I take the second row of bolus inputs, and I divide it by the second row. I set it equal to the second row divided by the very first parameter, which is our VC. So here I've converted the volumes into concentrations. Now, in order to add a time-varying input, we have to add a field called time-varying, just like in the constant situation, and just as in the rate of infusion situation. Every time-varying input is an element in this time-varying field, which is an array. Each element is going to have a name field. In this case, I'm calling it circadian, and it's going to have a value field. The first row of values is going to correspond to the times. So this is going to go from 0 to 50, and it's going to be evenly spaced at 500. And then I'm basically just defining the value as sine of that same time plus 2. Remember, this is very similar to the levels field. Instead of specifying switching levels, you're specifying different points in time, and then MATLAB's going to linearly interpolate between those points. So that's all. That's all you really have to change to the driver. Next, you need to change the simulate model. So you add a from workspace, because this is a time varying value. The name of this variable needs to be my time varying dot, and then the actual name that you specified on the previous slide. In this case, it's circadian. Then we have to add an input into the mux block. So we have length of parameters. Remember, that's 4, and then we have one more in this case, which is my time varying dot circadian. So that's all you have to change in the Simulink. Now we need to make some changes to our initial to the size of the inputs. So we need to set the number of inputs to 5. We have 5 parameters and 1 time varying input. And then we need to map that input, u of 4, to some variable in our comment block. So I called it circadian. And then we need to add that. Then we need to make changes to our differential equations to account for the presence of that variable. So we have DAT is equal to the rate of drug leaving the central compartment and going into the tissue space, the rate of drug leaving the tissue space, and the endogenous production, circadian. And then if we run the simulation, we'll see it. We have this sort of, you can see the bolus events occurring here, and then you can see the circadian input and its effects here. So that pretty much covers all of the different inputs that I think are important, that I thought would be useful whenever you're running simulations. The last thing we have is this exercise. So basically what I want you to do is to take the two-compartment model. So take the directory, two-compartment with bolus, make a copy of it, and then I want you to create a system where there's an extra compartment that allows for first-order absorption from some peripheral site. And then I want you to plot the profiles for both CP and the concentration of the drug at the peripheral site for a bolus of 50, administered first to the central compartment, and then run the simulation again and apply it to the peripheral site of injection. And then here are the parameter values you should use. You should stop the presentation now if you want to work on this by yourself. So this is our system, right? And if we look at our system, what we need to do is we need to modify the ODE for dCP/dt. We need to add the amount of drug going from the site of administration into the central compartment, and then we need to add a differential equation to represent the site of administration as well. We need to change the initial conditions we need to add an initial condition for the third compartment, and then we need to have our outputs be the CP and the mass of drug at the site of administration as well. So now we have 3 states, 5 parameters, and 2 outputs. Remember, we have the site of administration, we have the plasma compartment, and we also have the tissue compartment. We have the 4 parameters that we had before, and then we have the rate of absorption, Ka. So we need to make these changes, and we only have 2 outputs instead of 3 this time. Now we need to add an initial condition for the third state that we've added. Remember that the third state is actually an index of 2 in C, so we add in our initial conditions subroutine, we add this line, x0 of 2 is equal to 0.0. Remember, we can overwrite this anytime we want. We just have to give MATLAB something to start with. Then in our common block, we need to add a mapping for the 5th input to Ka. We also need to add a temporary variable, or create a temporary variable to hold the differential equation, and we also need to create a temporary variable to hold this extra state, the third state that we've created. Next, we need to modify our differential equations. Remember, we just added this component to the differential equation for the central compartment to account for drug absorbing from the site of administration, and then we have to add this ODE for the site of administration as well. And then in the ODE section, the last thing we have to do is we have to take the derivative we've calculated above and remap that to the derivative variable. Then if we go to the output section, we have our first output, which is CP, and our last output, which is AA. And remember that above this we have the common block where CP and AA have been defined. If we look at the driver file, we have our vector of parameters here, and then we have to reinitialize our initial condition at 0, 0, and then we have another state at 0. Remember, this third state represents the site of administration. Next, what we're going to do is we're going to specify our bolus inputs. We specify our bolus inputs for administration into the plasma compartment, which is state 1. And we store that, we run that simulation, we store that in sim output C for central compartment. Then we redefine our bolus inputs and we apply the 50. Now again, we're not dividing it by the volume because this is actually going into our third state, which is our site of administration. So this is the mass of drug being administered to the site of administration. So we've redefined the bolus inputs, and then we run the simulation again, and we store that in output A, in sim output A. So we have two different variables that have been created here. Sim output C, which has the simulation for the drug being administered into the central compartment, and then we have sim output A, which has the simulation for the drug being administered into the site of administration. Then what we do is we go through and we plot these things. In blue, we're plotting the drug being administered into the central compartment, and in red, we're plotting the drug being administered into the site of administration, or given IP. So here we see the IV administration, and we see the IP administration. And then we can also see the exponential decay for the IP administration, and then we see no drug present for the IV administration, which is what we would expect because there's no path going from the central compartment back to the site of administration. And this is the subplot for the lower plot. So if you're going to create a model by yourself, what I would do is I would begin by making a copy of the two compartment with bolus directory. Then what I would do is I would go through and I would modify the C file, the Simulink model, and the driver accordingly. And I have links and pointers to the different slides where we discuss these things. If you're going to start like a big modeling project, what I would do is I would start very simple, and then I would progressively add information. So especially when you're dealing with something new. So I would start by, if you want to do a PBPK model, I would start by modeling a tissue, just one tissue by itself. Develop the model for that tissue, and then maybe develop a model for a second tissue, connect them, see what their inputs look like, see what their outputs look like, see what the profiles look like. Do they make sense? Make sure each time you add some level of complexity to verify the outputs to make sure they make sense. And this can be done because you can actually look at the different components. So say you want to model, if you're doing a PBPK model, you can model, you can use the time varying input to model the different tissues independently, and then you can start sticking them together to see if when you put them together they actually work as you would expect them to. One of the really useful things I think about MATLAB is you can easily add any output you want to the output, and you can plot it. And also you have access to all of the individual states. So if your model isn't behaving as you would expect it to behave, what you can do is you can look at the outputs of the individual states, and if the individual states are not making sense, you can hopefully identify which state isn't making sense, and you can actually use this as a way to debug your model and to identify either typographical errors or structural errors within the model.